How do we solve this integral? The denominator reminds us of the Pythagorean theorem, because if we have a right triangle with hypotenuse 3 and side x, then the other side would be the square root of 9 minus x squared by the Pythagorean theorem. Say we introduce an angle theta in this triangle. Then sine theta would be x over 3, and cosine theta would be the square root of 9 minus x squared all over 3. We can rearrange these two equations to solve for x and for the square root we see in the integrand. The last bit of information we need is dx, the differential term, and we can get that easily by differentiating the equation for x, which gives us 3 cosine theta d theta. We are now ready to write the integral purely in terms of theta. The integral becomes the following. Notice that 3 cosine theta cancels out, and the integral becomes 9 sine squared theta d theta. To integrate sine squared, we'll have to use the double angle identity for cosine. Substituting, the integral becomes the following. Now, 9 over 2 is just a constant, so we can take it outside the integral. And the antiderivative is now very easy to find. The next step is to take everything back to x. But remember that we had sine theta and cosine theta in terms of x. Here we find theta and sine 2 theta. So how do we represent these in terms of x? Well, theta can be found simply by taking the inverse sine, and that'll give us arc sine x over 3. So that's theta done. To deal with sine 2 theta, we have to use the double angle identity, but this time for the sine. Replacing sine 2 theta by 2 sine theta cosine theta, notice that the 1/2 and 2 cancel out, and then sine cosine are precisely what we have in terms of x. So if we replace them with their equivalents, we get the following. We can now simplify this fraction, and then notice we have a 9 outside the brackets, so we can use it to clear the denominator of the fraction inside. This is just an extra step for simplification, but that's the final answer.